Once you understand the concept of chirality, the next skill is to be able to identify a chirality center. And so I'm using the term chirality center here, but you also might hear chiral center or stereogenic center or asymmetric center, and they're all pretty much referring to the same concept. A tetrahedral carbon, an sp3 hybridized carbon that has 4 different groups attached to it. And so let's look for some chirality centers in these molecules, and we'll start with this alcohol here. And so I'm going to go ahead and redraw this. I'm just going to go ahead and draw out all of the atoms here. So we have 4 carbons. The carbon on the left has 3 hydrogens attached to it. Right? So there's no way that's a chirality center. I need 4 different groups, and I have 3 of the same thing on that carbon. So that one is not one. This next carbon here, right, we have an OH, and then we also have a hydrogen attached to it. Right? So that's this carbon over here. Right? And this is a chirality center. We have 4 different groups attached to this carbon. So I'm going to go ahead and mark this carbon right here. This is a chirality center. There's a methyl group on this side. Right? So that's one different group. There's an OH group. Right? There's an ethyl group. And then there's also a hydrogen. Right? So go ahead and draw on that hydrogen. So there are 4 different groups attached to that carbon. So that carbon is a chirality center. So this carbon right here is a chirality center. Let me go ahead and draw in the other hydrogens, right? So I have 2 hydrogens on this carbon, so that's not a chirality center, right? I have 2 of the same thing bonded to this carbon, and then finally this carbon over here with 3 hydrogens, right? 3 of the same thing, so that carbon is not a chirality center. So 1 chirality center in this alcohol. All right, for our next example, let me go ahead and draw in the carbons, right? So we have 3 carbons. And the carbon on the left has 3 hydrogens bonded to it, right? So that carbon is not a chirality center. Same with the carbon on the right, 3 hydrogens, so there's no way it could be a chirality center. Let's focus in on this carbon right here. So let's think about the hybridization of that carbon. We know from earlier videos, right, that's an sp2 hybridized carbon with trigonal planar geometry. And so immediately you know that it's not a chirality center. That has to be sp3 hybridized, giving you a tetrahedral geometry. And we don't have 4 different things bonded to that carbon, so none of these carbons are chirality centers. So there are 0 chirality centers in this molecule. So that's acetone. All right, let's do a ring example. So let's do this ring example right here. All right, so let me go ahead and once again draw out. Let me draw it on the molecule this time. So we have a hydrogen here, right? We have 2 hydrogens on this carbon, right? 2 hydrogens on this carbon, all the way around our ring. So let me go ahead and draw in all of these hydrogens. All right, and then we look for chirality centers or chiral centers. All of these carbons, let me highlight them in magenta, all of these carbons have 2 hydrogens bonded to them, so that's 2 of the same thing. So there's no way those are going to be chiral centers. What about this carbon right here? So it looks like it might be a chirality center, right? We have a chlorine bonded to it, a hydrogen, and then we have these things going in opposite directions. But in actuality, this is not a chiral center. And that's because there's the same path around this ring here. So the hydrogen is like one different group, the chlorine is another different group, so that's 2 different groups. But if you go around the ring this way, and you go around the ring this way, it's the same path both ways. You hit a CH2, and you hit a CH2. You hit a CH2, and you hit a CH2, and then you hit a CH2. So it's the same path around the ring, so it's like 2 of the exact same groups bonded to that carbon. So another way of thinking about this is if I go ahead and focus it on that carbon at the top there again, so I have a hydrogen here and a chlorine here, and I draw in a molecule like that, right? So I took out this last carbon down here, so I'm leaving out the last carbon. One way to think about it is that's 2 of the same things attached to this carbon. Here's an ethyl group, and here's an ethyl group. So 2 of the same thing attached to that carbon, so this is not a chiral center. And so there are 0 chirality centers for this molecule. However, if we change things up, so let's look at this molecule now, we have a different path around the ring. So once again, we're focused in on this carbon, right, because we know we have a hydrogen bonded to that carbon here. So the paths around the ring, there's a different paths around the ring. Let me draw in the hydrogens once again. So there are 2 hydrogens on this carbon, right? Only 1 hydrogen on this carbon. And so if you go to the left around the ring, right, you hit a CH2 right here. If you go to the right around the ring, you hit a carbon bonded to only one hydrogen. And so it's a different path. And so it's like there are 4 different things attached to this carbon right here. So this carbon is a chirality center. All right, if we look at some of these other carbons, right, let me use red for this. All right, so if we look at this carbon right here, this carbon is sp2 hybridized, right? There's a double bond there, so it's not a chirality center. Same with this carbon. This carbon has 2 hydrogens bonded to it. This carbon has 2 hydrogens bonded to it. This carbon has 2 hydrogens bonded to it. And so there's only one chirality center in this molecule. All right, and then let's do one more example, which is just looks a little bit more challenging than the ones we've been doing. Right, so it's a little bit scarier looking. This is the ibuprofen molecule. All right, so let's go through this one by one. But let's start with this benzene ring here in the center. All right, so let's just start with this carbon right here. Right, so this carbon is sp2 hybridized, and as you go around the benzene ring, right, all of these carbons are sp2 hybridized. So that immediately means that these can't be chiral centers. Right, you need to be to have tetrahedral geometry to be a chirality center, and so those carbons are all out. Let's look at this carbon right here. Right, I know that there are 2 hydrogens bonded to that carbon, so that carbon is out. Let's look at this carbon. Well, I know that this carbon is bonded to 2 methyl groups, which is 2 of the same thing, and so that carbon is out. Let's look at this carbon. I know there are 3 hydrogens bonded to that carbon, so that one's out. All right, same with this carbon. So these 3 of the same thing. So none of these carbons over here on the left side of the molecule are chirality centers. Let's go over here to, let me use a different color for this carbon right here. Right, so I know that there's only 1 hydrogen bonded to this carbon. I'll just put it in right here. So let's think about the different groups. I have a methyl group right here. I have a hydrogen. Right, I have this carboxylic acid over here, and then I have my benzene ring over here, and the rest of the molecule. So that's 4 different groups attached to this carbon, and so this carbon that I've marked in blue here is a chirality center. So this is a chiral center, and go ahead and mark it. All right, let's focus in on this carbon on the methyl group. There are 3 hydrogens, so that's not a chiral center. This carbon right here has a double bond to it, so it's sp2 hybridized, so that cannot be a chirality center either. And so we have only 1 chiral center in this molecule. And so this is a very important skill to practice, to look at the carbons, think about what's bonded to them, and if there are 4 different groups bonded to that carbon, and it's a tetrahedral carbon, sp3 hybridized, then we can call it a chirality center or a chiral center or whatever term your professor wants to use.